welcome back. Welcome back. All right, so today I wanted to talk about the structured elucidation of polysaccharides. But that's a lot of big words, but what I'm trying to say is, okay, well, I have all this information. I know the reactivities of some kind of disaccharide or some kind of sugar that I got in my solution. Well, what is the structure of that sugar? And also, what is the structure of that disaccharide? And what are the different bonds that we can make? So, in terms of what we want to look for, there are usually or generally 4 characteristics that we want to look for when we look at our molecules. The first one is our hydrolysis product. And so for hydrolysis, it just tells us what sugars make up the polysaccharide, right? Well, I could have a sugar with fructose and mannose and galactose, or glucose, only glucose, or I can have mannose and galactose, and I can have all of these different combinations. But what hydrolysis products tells us is it literally just tells us what sugars make it up. And so if I say a hydrolysis product comes out with galactose and glucose, well, in that case, the only sugars that are going to be present in your disaccharide or polysaccharide are going to be galactose and glucose. All right, so for the second characteristic we want to look for are just any reactions with enzymes. Okay, so what I mean by this is, okay, let's say I have an alpha ACE, right? I'm not going to name the sugar, just some alpha ACE. Well, that will break only alpha linkages, whereas beta ACEs will break beta linkages between different sugars, right? But also the key point that I wanted to stress here is that the name of the enzymes will tell you which sugar has the anomeric linkages. In terms of picture-wise, how I can explain this, we have an alpha glucosidase right over here, right? Okay, so this is an ACE, so we know it's some kind of sugar. Glucose means, okay, well, it's going to break alpha linkages of glucose. So that's one way we can tell where the anomeric linkages of the sugar is going to be. But no, it will only break alpha linkages. So in these 2 examples right here, this is going to be an alpha linkage. And then in this case, this is going to be a beta linkage. But the thing is that this is good. This will be reactive towards that enzyme, but this will not. So keep in mind what the name of your enzyme is, as well as if it's alpha or beta. All right. Okay, so then the last 2 I'm going to be talking about is reducing and non-reducing. And so really what I'm trying to say here is, does it react with the Tollens reagent or the Bendix reagent, or even just bromine H2O, bromine water, right? And if it's yes, then it at least has 1 free anomeric C, at least 1. But if it doesn't, right, if it doesn't react with any of those, then it doesn't have any free anomeric carbons. So for example, let's say I have this sugar right here. Let me take this out. Must have drawn it terribly. All right. Okay, looking at anomeric carbon on this one, and even this disaccharide right over here. I'm not going to draw the rest of the OHs, but looking at just this, we can tell, okay, this is a free sugar because there is an OH right here, as well as in this case, there's an OH on the anomeric carbon. So those are considered free, or at least free anomeric carbons. Whereas this other anomeric carbon right here is not free because there is no OH and that O is attached to another molecule. However, if you were to react both of these sugars in your molecule, then these would both be considered reducing sugar. Well, the reason why is because, well, hey, they both have at least 1 free anomeric carbon. So in this case, we couldn't really tell the difference between these 2, but just note that that's one way we can tell. If it doesn't react, it's non-reducing, meaning that that's a huge hint saying, okay, none of these sugars have any anomeric carbons that are free at least. Okay, the last one is where we can start seeing where the bonds are going to be made. And so it's going to be, first we're going to methylate all of the free OHs, all of the free OHs in our original molecule, right? Not any of the hydrolysis product, not any of this, just take our molecule, turn all the free OHs into OMEs. And then the next step is we do hydrolysis, which will cut the sugar bond. But then this also shows us 1, where all the anomeric OHs are, and 2, where any other attachments are. Because we can make carbon or glucose sugar bonds on an anomeric carbon and something else that isn't another anomeric carbon, especially if it's reducing sugar. Okay, so let's look at an example of how we can do this. All right, so we want to find out the structure of melibiose, right? Okay, so we have 3 pieces of information that we can get from this. Okay, so 1, it reacts with the Collins reagent. Okay, that's pretty good. So we know that this is some kind of reducing sugar, meaning it has at least 1 free anomer. Okay, 1 free anomeric carbon. All right. The second one that we're going to be looking at is, okay, well, it hydrolysis with alpha galactosidase. Okay, so alpha, okay, good. This is an alpha linkage. And it's an alpha linkage on a galactose molecule. Interesting. And so this gives D-galactose. Huh. All right, interesting. So we know that at least this carbon right here has to be an alpha OH or an alpha linkage. And then in this case, it also gives D-glucose. Interesting. So this OH on the galactose will react with some kind of OH on the glucose, but we don't know where. All right. So then the last step is we first do the methylation, all right? Methylate all the free OHs in our original molecule. And then we hydrolyze it, giving us the following products. Okay, so we get this galactose. So this is some kind of, 1, 2, 3, 4, tetramethyl galactose. And in this case, this is just a trimethyl glucose. Okay, now what does methylation, or what does the hydrolysis do? Well, it identifies all the anomeric carbons. Okay, well, that's good. Anomeric, anomeric. And it also tells us where other attachments were. Okay, well, what's interesting to note is that there's this OH right here. So this OH could have been another attachment point to the other sugar on glucose. Okay, so how can we use all this information? So we know it has at least 1 free anomer. Okay, it hydrolyzes with alpha galactosidase. So we know that the galactose is the end that doesn't do the reaction, and it's an alpha linkage, and it also produces glucose. Okay, interesting. And the last part is that methylation, okay, turning all the free OHs into OMEs, and then taking the anomers, turn that to OHs. But also we've identified this weird OH that didn't react with methyls. Okay, well, in terms of how we can actually show all the information, well, first off, we know we have to have this galactose in our molecule. Okay, so we know there has to be some kind of galactose. All right, now remember, using the information from step 2, it's an alpha galactosidase, meaning that this linkage between here and the next sugar is going to be an alpha group, is going to be alpha. But okay, so where are we going to actually attach to the next sugar? Well, we know that, okay, if this is not free anymore, then there has to be at least 1 free anomer. So looking at glucose right over here, or the glucose that we had, it can't react with the anomer, or it can't be attached to the anomer because it needs to be free. However, out of all these other ones on this trimethyl glucose, 2, 3, and 4, those are all methylated, but this CH2OH is still an OH. So that signifies where it's going to be attached. So this O coming off of this will attach to the CH2 onto our glucose molecule. So let me draw that like this. And then it doesn't really matter what this last anomer, because it's an anomer, but this last one has to be an OH. And well, there you have it. This is melibiose. Okay, let's check to see if everything is correct. Okay, the first factor is there has to be a galactose. Okay, check. There has to be a glucose. Check. All right. On galactose, it has to have an alpha linkage. Well, that's an alpha linkage. Check. And then we need to see where it's going to be attached to. Well, this is for the methylation and the methylation step. well as all of this. Well, looking at our product right here, this OH, this OH, this OH, so 2, 3, and 4 are all free. 2, 3, 4, and 6, those are all free. Okay, that's good. And also all the anomeric carbons will turn to OH. So, well, anomer, anomer. All right. Well, in that case, there you have it. So that's one way we can look and use all the chemical information to actually get the structure of a disaccharide or a polysaccharide.